All right, we're going to go ahead and dive into the second lab for Module 3. Again, there is an extensive supplemental reading that you definitely want to look through that is posted in the lecture module. So go ahead and read through that. This presentation is just going to cover some of the quick things that you'll need to know regarding the atmospheric profile. So regarding the basics for the atmospheric profile, let's take a look at pressure. Pressure, more or less, is the size and motion of the number of air molecules that exist or that exert force on something. And so just like when you dive deep into a pool of water, the deeper you go, you're going to feel more pressure. You're going to feel that pressure on your eardrums, and more or less the same thing is at play here. The closer that you have atmosphere to Earth's surface, that is going to have a higher amount of atmospheric pressure than a section of atmosphere that is farther from Earth's surface. And you can see that right here. This is attempting to represent the amount of atmosphere in a specific area. And so you can see close to Earth because the amount of gravity that's pulling it towards Earth, also the weight of the atmosphere that is pressing down on the atmosphere itself. There is more pressure, right? More air molecules in a smaller area closer to Earth's surface, and the farther you get away from that, there's going to be less air pressure. And this continues to decrease the farther you go until you get all the way up to space. So there's more air pressure closer to Earth's surface, right? There's more density, and the pressure thins out and becomes less the farther away you get from Earth's surface. This next graph shows the exact same concept where you can take a look at pressure, which is measured in millibars. And as we increase in altitude, right, as we get further and further away from Earth's surface, which is down here at 0, you can see how the pressure decreases. So this is the millibars, right? So at Earth's surface, we have over 1,000 millibars. And the farther up you go in Earth's atmosphere, as we gain in elevation, you can see how the air pressure decreases significantly until it basically flattens out. And the reason that this is important is because the amount of air pressure directly impacts the amount of heat that we are feeling throughout the atmosphere, and that's where we have to figure out the difference between heat and temperature. So it's really important to know that temperature is not the same thing as heat. Temperature is a measurement of kinetic energy, right? That is moving energy. So really, temperature measures how fast or slow a molecule is moving. So if we have a molecule that is moving at a really high speed, it can have an incredibly high temperature, but that does not correlate into heat. Heat is created when kinetic energy happens. That means when one molecule is transferring its energy to another, basically when molecules are colliding, that is what creates heat, the heat that you and I can feel. So temperature is not the same thing as heat. And the reason this is important is because you can have areas in the atmosphere with a really high temperature. You'll have molecules moving at incredibly high speeds, but if they have no other molecules to hit, they are not creating any heat, right? So where density is incredibly low and there's very low air pressure, that means that there will be very little to basically no heat existing at that temperature, or excuse me, at that elevation. Again, this is important to understand as we take a closer look at the atmospheric profile, as I jump back up a slide, because we're starting down here at the bottom with the troposphere, moving through the stratosphere, mesosphere, thermosphere, and then it goes on to the exosphere. And so depending on where we are in altitude or elevation, moving further away from our surface, we are going to have different characteristics at play. So let's take a closer look at the atmospheric profile, starting at the troposphere. All right, starting with the troposphere, which is the area of atmosphere that is closest to Earth's surface, you'll notice that 90% of all of Earth's atmosphere is within the troposphere. So you know as the density and air pressure decreases as we go up in altitude, 90% of all of Earth's atmosphere, right, all that density, all that pressure is going to rest within the troposphere. Another really important line to pay attention to is this yellow line. This is the temperature profile, and so you can see how the temperature is decreasing, right? Here we have 0 degrees Celsius, 32 degrees Fahrenheit. And so as we go up in elevation, as the air density decreases, it gets colder. And then up here in the stratosphere, the temperature increases again, but due to the lack of air density, there's no real heat that we're going to be able to feel. So again, the temperature swings, which is just the movement of molecules, is really what's changing here, rather than the amount of heat that exists. So even up here, when we are basically at the brink of space, you can see that the temperature is 22,000 degrees Fahrenheit, but we wouldn't burn to a crisp up here because, again, there's no heat, there's no kinetic energy happening with those molecules, where those molecules are not hitting each other. After the troposphere, we're taking a look at the stratosphere. So temperatures increase with altitude, but what is really important about the stratosphere is that we have the ozone layer, which is something you may be familiar with at this point. If not, the ozone layer is arguably one of the most important layers in our atmosphere, as it helps to absorb the UV radiation that comes in from the sun. Ozone is triple oxygen, so it's O3. So the function of the ozonosphere, which is a very thin layer that resides within the stratosphere, right? It's a part of the stratosphere. This is where that ozone, O3, exists and absorbs a lot of those harmful ultraviolet energy, those ultraviolet rays that are coming in from the sun. So what it does, function-wise, is that the ozone layer, again, protects us from that. It absorbs a lot of this radiation, but through things like CFCs, these are chlorofluorocarbons. This is chemicals that get emitted through things like refrigerants or propellants, basically float up into the atmosphere, and they quote-unquote attack the ozone and they break it down. So the mixture of these chlorofluorocarbons plus the ultraviolet light or the ultraviolet radiations that are coming from the sun break down to create chlorine, and that chlorine breaks down and kind of erodes that ozone. So that protective layer, you can think of it as Earth's sunscreen, basically gets broken down, and that means that there are more of these harmful radiation waves of radiation coming into Earth's atmosphere and generally causing, even for you and me, more skin damage due to the protective layer being eroded over time. So that's one important component of the atmosphere, the ozonosphere, part of the stratosphere, something that you definitely want to know about when discussing atmospheric profiles. But okay, so moving on to the mesosphere, again, you can see that the temperatures are decreasing as we continue to increase in altitude. Again, this is due to a lower level of atmospheric density. There are less molecules that are not only absorbing the solar radiation, which would cause them to move faster as they become more energized, but there's also less molecules at this area in the altitude. At this area in elevation, so that there is no kinetic energy being transferred, thus no heat. The thermosphere, again, where the temperature profile is showing extremely high temperatures. So these molecules that exist out here are incredibly high in temperature. They're moving incredibly fast, but again, heat is not generated because they are not transferring any of their kinetic energy. So it's not hot because of the low density. But keeping the temperature profile in mind, that is important because that is what we are looking at for today's labs, where you are going to have to accurately measure and decipher whether or not the atmospheric temperature, the atmospheric profiles are accurate or not. So really what you're going to have to do is take a look at the temperatures. Here is temperature and at specific elevations, and use these graphs to make sure that everything is aligning properly. So this is the example graph of a atmospheric profile that would be accurate for the data provided down here in this graph. So surface, right, that's our sea level. That is where we're starting down here in our elevation. That is 0 kilometers. or 0 miles above Earth's surface, and our temperature is 15 degrees Celsius. So keep in mind that we're looking at Celsius and Fahrenheit exist on the same map, and you want to pay attention to the units that you're using in order to measure these scales. So the next point, right, for the troposphere, 20 kilometers above Earth's surface, our temperature is going to be negative 15 degrees Celsius. So we want to jump over here and find our kilometers above Earth's surface, 0, 10, 20 kilometers, scooch on over and find our temperature, negative 15 degrees. So we know that this point is also correct. So simple, go through here and make sure that all of the points match up to the data existed at the bottom of the graph so that you can accurately measure temperature profiles. So this is our lab for today, and hopefully the atmospheric profile mini lecture taught you something new. All right, get to it.